In the previous video, we discussed the vector space Rn, and we saw that it has 10 properties which we focused our attention on, properties of the structure of Rn in terms of addition of vectors and in terms of multiplying a vector by a scalar. A scalar is just an element from R, a number. Okay? And here is the list of these properties. I left it here on the board. And what we want to do now is define a totally abstract notion of a vector space, which is going to be a structure that is comprised of the following four things. There's going to be a set of elements called the vectors, but now they're abstract. You can't think anymore of well, you can think of those as examples, but they're not necessarily going to be n tuples of numbers. Okay? So those are the vectors, the elements. There's a field from which your scalars are coming from. It can be any field, Q, R, the complex numbers, C, or any finite field. Any field, we're going to denote it by F. And there are going to be two operations. How you add vectors and how you multiply a vector times a scalar. How you scale a vector. Okay? And there are going to be 10 axioms. Okay? We're going to require that this structure satisfies all these 10 properties. Okay? I'm not going to erase here. I'm going to rewrite them because I want to I want to rewrite them, and the reason is that there's a more compact way of doing it. Okay? And you have to think for a minute. Look at properties 1, 3, 4, 5, and 6. Look at properties 1 through 6, not including 2. Do you agree that those 5 properties, the first 6 without 2, only involve the addition? Do you see that? Okay, they only involve the addition. And these properties are precisely the same properties that addition satisfies in a field. Do you see that? Right? And in fact, they're precisely the 5 properties of what we called a group. A group is a set of elements that satisfies precisely properties 1 through 5, not necessarily with 3. If it satisfies 3, then it's what we called an abelian group or a commutative group. Okay? So if you happen to forget the notion of a group, I'm just going to tell you what it is right now, and you can look back at I think it was in one of the very first videos of this course, what is a group? Okay? But a group is merely a set that satisfies properties 1, 4, 5, and 6. And a commutative group is one that satisfies 3 as well. Okay? So there's one operation, addition. It's closed under addition. Addition is commutative. That's a commutative group. Addition is associative. That's property number 4. There's an additive identity. That's property number 5. And there are additive inverses for every element. That's property number 6. Good? So this is what I'm going to write now. I'm going to write the definition of a vector space. Okay? V is called a vector space over, that's the term we usually use, over a field F. F is going to be our field. If V is an abelian group and I'm going to remind you now, an abelian group, what this means. So abelian group means that, so this is in parentheses, it's just a reminder, plus operation satisfying closure. Addition is closed. So you add 2 things, you get another element, right? Closure. This is a LO, not a D. Now this is a CL, not a D. Wow. Satisfying closure, associativity, commutativity, that's being abelian. Additive inverse, well, it's just additive, so plus inverse and 0. Okay, so is it clear what I'm indicating by this? Okay, it's really properties 1, 3, 4, 5, and 6 of that we saw in Rn. Okay, so it's an abelian group with an additional operation, an operation of multiplication, multiplication. Can you believe that in Hebrew the word for multiplication is 3 letters? Multiplication by scalars, by a scalar, okay, a scalar is an element of f. Okay, so there's an additional operation of multiplication by a scalar such that, and now all I have to list is the 5 properties of multiplication by a scalar. Okay, so the first property, such that 1, and I'm going to list it abstractly. Remember, it's no longer Rn and it's no longer R. So alpha times v belongs to big V. Big V is our vector space for every alpha in F and for every V in V. Make sure your little v's and big V's are little and big. Otherwise, you'll get very confused now. Okay? So what is this property number 1? Exactly, it's the closure, right? This is saying that multiplication of a vector by a scalar is closed. You get again a vector. Okay? Property number 2, 1 times V equals V for every V in V. Good? 1 is well defined. It's a field. A field has a multiplicative identity. That's this 1. And when you multiply a vector by 1, you get the vector itself back. And remember that these vectors are no longer n-tuples. These could be matrices or functions or solutions to some system or whatnot. Okay? 3. So these are abstract axioms now. Okay? This is how we define a vector space. 3, alpha times v plus w. And note that being elements of the vector space is usually encoded in denoting them by little letters of the range UVW. Okay? So I'm not going to add these arrows on them. The arrows are more reserved for tuples from R2 and R3 that we're used to seeing. Okay? So this could be a function now. Okay? So I don't want to put an arrow on it. Okay? So alpha v plus w equals alpha v plus alpha w for alpha plus beta v equals alpha v plus beta v, and 5 alpha beta v equals alpha beta v, and these 3 are for every alpha beta in the field and for every v and w in the space. Good? So this is the abstract definition of a vector space. The structure has 4 ingredients. The space itself, the elements, those are the little v's and the little w's. The field, the alphas and the betas. Okay? The plus operation, satisfying 5 axioms, which is here encoded in one word saying that it's an abelian group. Okay? And the multiplication by a scalar operation, which satisfies these 5. axioms. Okay? And I'm just going to mention it again. We mentioned it before. There could be more structure. There could be more axioms, but that would yield things that are more than just vector spaces. So there's a notion of a normed space, or a metric space, or an inner product space. And all these things involve further structure that is not relevant to this. Okay? It goes beyond. So we're only looking at these 5 properties plus 5 properties. Okay? Only at addition and scaling and scalar multiplication. Good? Okay. So let's start writing some examples. Okay? So examples of vector spaces. So examples. So example number 1 is Rn. We know it's an example because we studied it separately and revealed the properties from Rn, right? But if you want to claim that something is an example, what do you have to do? Just like when you want to claim that something is a field, what do you have to do? You have to see that all the axioms are satisfied. You have to check them one by one. If they're satisfied, good. It's a vector space. Okay? So this is the first example. Let's look at another example. Look at all matrices of the same size, of a fixed size. So M by N matrices, let's say over R. So this is notation that we used. So these are only matrices of size M by N, M rows and columns, with all the entries taken from the field R. Okay? I claim that this is a vector space. Okay? So I'm not going to write everything because it's going to take too long and it's really easy to see it in your head. But if you need to play around with it a bit and get the feeling better, do it. Don't be lazy to get your hands dirty. Okay? But let's look at the properties, all 10 axioms, and see that it's indeed a vector space. Okay? So first of all, what are the elements? The elements are M by N matrices. Those are the little v's. Okay, so the little v's are no longer n tuples. The little v's are now M by N matrices. If it's difficult for you to think M by N, think 2 by 3. Okay? What are the scalars? Well, R. If we're looking at matrices where the entries come from R, then we're usually going to take the field to be R. Okay? So those are the scalars. What's the operation I did? What's the addition operation?
Addition of matrices.
Right, addition of matrices. Right? And what's the scalar multiplication? Multiplying a matrix by a scalar. Right? So let's look at let's look at the definition. There's a field F, there's the vector space V. These are M by N matrices. This is R now. Is it an abelian group? So is there a plus operation? Yes, there is a plus operation. Is it closed? When you add an M by N matrix to another M by N matrix, do you get an M by N matrix? Yes, the operation is closed. Okay? And it's not trivial that any operation is closed. If you would, for example, it's not relevant to this, but if you would multiply 2 matrices, you often alter the sizes, right? An M by N matrix, you can only multiply by an N by L matrix, and you get an M by L matrix, right? So not every operation is automatically closed. Do you agree? Okay? But addition of matrices of the same size is closed. Put a check. What about associativity? Is addition of matrices associative? It is, right? Because it's done element-wise. Is addition of matrices commutative? Is it true that A plus B, and now think of the elements as capital A because it's a matrix, and capital B. A plus B is the same as B plus A, right? It's not true for matrix multiplication, but that's not what we're talking about. We're only talking about addition, right? Okay. Is there an additive inverse to every matrix? Well, first of all, is there a 0 matrix? Yeah, there is. All the entries are 0. And is there an additive inverse to every matrix? Given a matrix, can you find another matrix such when you add them, you get the 0 matrix? Yes, you just flip the sign of all the entries. Do you agree? Okay. So matrices of the same size, a fixed size M by N, are an abelian group. Okay. Is there a product of multiplication of a matrix by a scalar? Yes, there is. When you multiply a matrix by a scalar, do you again get a matrix of the same size? Yes, you do. So it's closed. When you multiply the scalar one, this is not the scalar matrix, it's just the number 1 times a matrix, do you get back the same matrix? 1 times a matrix is the same matrix. Good. And do these 3 properties of all kinds of associativity and distributivity laws, do they hold? And the answer is yes, we know that. We mentioned that as properties of addition of matrices and scalar multiples of matrices previously, right? If you do 5 times the matrix A plus the matrix B, it's 5 times A plus 5 times B. And you can verify that again element-wise to be convinced. Okay? And likewise for 4 and 5. Okay? So M by N matrices are a vector space. Good? Okay. Before we give more examples, let's list some more properties. Okay? So more examples. More examples soon. More properties. So what do I mean by properties? Well, if I look at Rn, I can just say, hey, it satisfies also that, ... Okay? But here, now I'm holding in my hand something completely abstract. All I know is that it satisfies these 5 axioms plus being an abelian group, which is another 5 axioms. Can I say that it satisfies more things? And the answer is yes, but I have to prove it. Okay, I can't check it on examples, I have to prove it. Okay, so it's going to be called a theorem. It's not going to be a difficult theorem, but it requires proof. So let V be a vector space. Let's abbreviate vector space like this, over, and I have to mention what the field is, so the field is going to be F. Then, so the first property is going to be that 0 times V is 0 for every V in V. Now there's something tricky here. What is this 0? Scalar. Right, this is the scalar 0, because it's multiplying a vector. It can only be the scalar 0. There's no other notion of multiplication, right? What is this 0? This is the vector 0, right? We're not putting arrows, but we should see that these two zeros are completely different. This could be the 0, 5 by 6 matrix, whereas this is just the number 0. Okay? You could. It would make life a lot, well, not harder, but slower, because I'm going to have to put tons of arrows over everything, and it's not necessary. Okay? Sometimes things, just like you don't put a dot here and you know that this is multiplication, sometimes you get things that are not explicitly written, but they're implicit and they're easy to note and to understand, and you don't just need to specifically emphasize them. Okay?
Was our previous use of the arrow just to help understand, like it was unnecessary earlier too? Matrices?
It was not, yeah, you could get along without arrows at all. Some people do that, okay? In the world of vectors, in terms of vectors of Rn, it's very common to use arrows of different types. Some textbooks just do the vectors in bold. There are many, many different ways of indicating that, but really we'll see. Well, at the beginning it's going to take getting used to, like any new thing. But you'll see that when you see something like this, it would be obvious that this is the scalar 0 and this is the vector 0. Okay? And by the way, if it still confuses you, it's fine. Put a little arrow here to remind you. That's fine. Okay? Okay. Now, it looks obvious, right? You multiply 0 times a vector. Of course you get 0. What else are you going to get? But it's not one of the axioms. Okay? So the fact that it's obvious here and it's obvious here doesn't make it true. You need to prove it. And what can you use in order to prove it? Only the axioms, right? That's those are the rules of the game we're playing in abstractizing stuff. Okay, here's another property. alpha times 0 equals 0 for every alpha in F. If you take the 0 vector, multiplied by whatever, you're going to get the 0 vector back. Okay? Looks very convincing, but that's not a proof. You need to prove it. Property number 3, alpha v equals 0 implies that alpha is 0 or v is 0. So if you take the product of a scalar times a vector and you get the 0 vector, either alpha was 0, this is the 0 scalar, this is 0 in F, or v is 0, this is the 0 vector, and this is the letter O in English. Good? Okay, let's prove. I'm not going to prove all of them. Maybe I'll leave one for you to prove on your own, and I'll do 2 and 3, just so you get the idea. So I think by now we can erase these properties of Rn, because we rewrote them abstractly, and now we have an extra board. Okay. So let's do some proofs. So proof of 2, for example. So we want to show that alpha times 0 is 0. And our hands are tied. We can only use the axioms. We've been playing these games when proving things about fields, right? We're already not completely puzzled by doing things like this. And still, in the beginning, when you see stuff like this, it looks kind of, what's going on here? Why are we doing this? Isn't it obvious that multiplying something by 0 gives 0? No, it's not. Okay, you need to prove it. Good? Everybody happy? Smile. Thank you. Okay, so alpha times 0. Do you agree that this equals alpha times 0 plus 0? Why? You can't just agree because it looks convincing. You have to show why this follows from the axioms. Because 0, this is the vector 0, has this property that whatever you add it to, you get back the thing you added it to, right? So if you take 0 and add a 0 to it, you get 0 back. Do you agree? Okay? That's the property of the 0 in an abelian group. Okay? The property of the additive identity. Okay? So this holds. Now, I'm going to use one of those distributivity properties, number 3 in the definition. This equals alpha times 0 plus alpha times 0. Do you agree? Okay, so this is, again, I'm concretely saying in each step what I'm using, what I'm relying on in order for this to hold, only by the definition. Okay? Good. So now that I know this, this implies that if I take alpha times 0 and I add to it its additive inverse, and this additive inverse exists. Any element has an additive inverse. So maybe we need more parentheses here. It's plus minus alpha 0, right? Every element has an additive inverse. That's a property of an abelian group. On the one hand, what is an element plus its inverse? 0. Do you agree? On the other hand, this equals, and now I'm going to replace alpha times 0 by 2 of them. Okay, and I can do that because of what I showed here. So I get alpha times 0 plus alpha times 0 plus minus alpha times 0. Do you agree? Okay? Now I'm going to use the associativity law for addition. So instead of writing like this, I'm going to write alpha times 0 plus alpha times 0 plus minus alpha times 0. Here I used associativity of addition, which is part of being an abelian group, part of being a group. Okay? And what is this now? 0. It's an element plus its additive inverse. So this just equals alpha times 0 plus 0. And adding 0 is like doing nothing. That's again a property of being 0. So you get alpha times 0. So if you look at the two ends, alpha times 0 is 0. Okay, we proved it. Now we know that it's true. Once we proved it, we know that this is true for any vector space in the world. Ones you think of and ones you haven't thought of yet. Clear? It's a property. Okay, and it's as valid as any of the axioms because we now proved it. We can use it. Okay, let's prove number 3. Do you agree to the statement that this is not hard, it's not difficult, but it's a bit confusing at first?
It's not intuitive.
It's not something you're used to do, in fact, right? You're not used to saying, hey, 0 times something is 0. I need to prove that. Okay, because it's something new. Okay? In your head, you're always running examples of things you're used to, but it's abstract. It's going to cover many, many things that you're not used to yet. Okay, so you have to prove it. Okay, let's prove number 3, that this, we did, number 3 was, look here, that if we multiply a scalar times a vector, and we get 0, then either the scalar or the vector were 0. This, we proved something very similar when we talked about fields, saying that there are no 0 divisors in field, that if you, in a field, if you multiply 2 elements and get 0, one of the elements has to be 0. And the proof is going to be very similar. If you look back at that proof, almost the same. Okay? Just different because now this is a vector and this is a scalar, but the idea is very, very similar. Okay? Let's do it. So let alpha times v equals 0. Does anybody remember how we did this? Okay, so I'll remind you, we first assumed that alpha is 0. Okay, so we need to prove that either alpha is 0 or v is 0. If alpha is 0, we're done. Duh. Right? Well, if alpha is 0, then alpha is 0. That's what we want to prove. So we need to prove, so saying that one of them is 0 is saying, okay, suppose alpha is not 0, let's prove that v is 0. Do you agree that that would prove it? So if alpha is not 0, then, and the reason I'm doing this, the reason I'm separating this case is also useful for what I'm going to write now. Remember that alpha is an element in the field. Okay? If it's not 0, it has a multiplicative inverse in the field. It has a 1 over alpha, or an alpha to the minus 1. Okay? Then there exists alpha to the minus 1 in F. There exists a multiplicative inverse of alpha. Do you agree? Okay? Such that, and now we can write, what is V? On the one hand, V is 1 times V. That is one of the axioms. That's axiom number 2. So we can use that. Instead of 1, we can replace 1. 1 is the scalar 1. We can replace 1 by alpha minus 1 times alpha. For any element in the field, if you multiply it by its multiplicative inverse, you get 1. Do you agree? We're just here using a property of the field, not of the vector space. Now we're using the property of the vector space, property number 5, that we could, that this product, here it's a product in the field and here it's a product in the vector space, is associative. So we can write this as alpha inverse times alpha v. Do you agree? But what is alpha v? Alpha v is 0. That's the whole that's the assumption of what we're trying to prove. So this is alpha inverse times 0, the 0 vector. Okay? And what is alpha inverse times 0? Why? Which axiom does it follow from?
It's the second.
Very good. It's not an axiom. It's part 2 of the theorem which we just proved. That any alpha times 0 is 0. So this equals 0 by part 2 of this theorem that we just proved. So if you again look at the ends, if alpha is not 0, then v has to be 0.
When you pointed out that if alpha equals 0, we're done, are you basing it on the first one?
No. I need to prove that either alpha is 0 or v is 0. If alpha is 0, we're done. Then either alpha is 0 or v is 0, right? If alpha is not 0, then, well, we showed that v has to be 0. Do you agree? It's logic. It's not basing on any... You need to prove that either alpha is 0 or v is 0. Okay? If alpha is 0, you proved it.
Well, it's the same thing vice versa. If v is 0, according to...
Well, you can't say if alpha is 0, we're done, and if v is 0, we're done, because what if none of them are? Then you didn't prove anything. But that's not what I did. I said if alpha is 0, we're done. If it's not 0, and that's the complementing case, there are only these two options. Either alpha is 0 or it's not. If it's not, then v is 0. So we exhausted all the possibilities, and we showed that in each of the possibilities we get either alpha 0 or v 0. Good? Okay, so try to do number 1 on your own, and also try to do, so here's homework. Try to show, for example, that alpha times minus v is the inverse of the vector v in the group, in the vector space, equals minus alpha times v. Minus alpha is the inverse of the scalar alpha, okay? And this equals minus alpha v. Okay? Try to show it using only the axioms, the definition, plus what else can you use? Right, you can use the new 3 properties that we listed and proved. Okay? Try to do it. It really feels at the beginning like playing a game. But it's a game you need to play by the rules. Okay, good? Okay, let's write more examples of vector spaces. So more examples, I promised you, so let's do them. And once again, I'm not going to, for each example, explicitly write all the 10 axioms. Okay? I'm going to kind of wave my hands and try to convince you that, well, they hold. But if you feel that it's too fast, if you feel that you need to think about it some more, I think that's probably what you should feel. It's the natural thing at this stage. You need to think about it some more. You need to take each example and run it through the definition and verify that indeed everything holds. So here's another example. We had 2 of them, so let's continue the enumeration. So example number 3, often denoted f to the n. Okay, so these are just n tuples over f. Okay, so we had r to the n, Rn, but you could have, for example, c to the n. N tuples, okay, column vectors, where all the entries are complex numbers, a plus ib. Okay, so that's also going to be a vector space over the complex numbers for exactly the same reasons. Okay, there's addition of complex numbers. The addition is, there's addition of column vectors where the entries are complex numbers, just like addition of matrices where the entries are complex. Okay, everything works. You just have to verify it, to think about it carefully, one by one, and be convinced. Okay?
Do you mean f is a specific field or a general?
Yeah, for any field f. Over the field f. So in this course, I said it several times, in this course, the world of fields that we're going to make use of is rather dull. We're usually going to only consider R and C. The real numbers are the complex numbers. Those are going to be the F's that we're usually going to use. Okay? But there are many, many more fields, and you may encounter them in further studies. And when I say something and put an F, it means that it would work just the same for any field, even if you don't verify it right now. Okay? Okay. Number 4. So 3 and 4 are just expansions of 1 and 2. Take matrices, m by n matrices, over a field F. Not necessarily over R. Again, it's going to be a vector space. And I'm not going to run through all the properties because it's the same statement. Okay? But here are some things that maybe are new. So for example, what we denote by F with X in brackets. Okay? This is notation for, so let's write here, m by n matrices over F, where all the entries are from F, and it's I'm not writing it, but it's implicit and it's well understood what the addition is, what the scalar multiplication is, right? Everything is clear. We add matrices just like we add matrices. Okay, so this is polynomials over F. Over F means that the world of scalars that we're using, all the coefficients, all the roots, everything, are from the field F. Okay? So I'm claiming that this is a vector space. Okay? Why? Well, let's think. Is there a notion of addition of polynomials? Yeah, we know how to add polynomials. When you add 2 polynomials, do you get a polynomial? Yeah, good. When you add 2 polynomials, does it matter in which order you add them? No, it's commutative. Is there a 0 polynomial?
0.
Yeah, 0 is the 0 polynomial. You add it to any other polynomial, you get the polynomial, right? Is there an inverse to a polynomial? Is there, given a polynomial, can you find another one such that when you add them, you get 0? Yeah, right? You just put minuses on all the coefficients. Do you agree? Okay. Is there, now we need scalar multiplication. If I multiply a polynomial by a number, do I get a polynomial again? Yeah, I do. If I, is it true, do the distributivity's law hold? So if I take 3 plus 5 times a polynomial, is it the same as 3 times the polynomial plus 5 times the polynomial? Yeah, right? Is 1, the scalar 1 times a polynomial, does it give back the polynomial? Yeah. So do you see that everything holds? Okay? Good. Let's put a 5 prime here, and this is going to be, or let's call it a remark. Remark, before we continue this list, remark. There's also notation, so maybe let's leave the notation for a minute, but polynomials, one could ask, suppose I take only polynomials of degree 7. Not all, this is all the polynomials, all of them. Suppose I take only polynomials of a fixed degree, of degree n. Only those. Is it a vector space?
Yep.
Nope. So why not? So you're thinking, what's going to change? Well, we just mentioned exactly all the properties and we saw that they hold. So my claim is one of them is going to fail. There's one property that's going to fail.
Closure.
Very good. Closure under addition. You can take 2 polynomials of degree 3. Suppose one starts with 3x to the power 3, or let's not use 3 all the time, 4x to the power 3, and the other one is negative 4x to the power 3.
Yeah, but you can
Their sum is no longer a polynomial of degree 3. Do you agree?
It's 0, but you can say that it's 0 plus 0 times...
That's another thing that fails. 0 is not a polynomial of degree n.
You can say that it is, but...
No, you can't. Degrees of polynomials are well defined. 0 is not a polynomial of degree n if n is let's say 3 or 4 or 17. Okay? So some of the properties of being a vector space, of being a vector space fail. Okay? 0 is not there. And you can add 2 of them and get a polynomial of a different degree. Okay, so closure for addition fails. Okay, so this is not, are not a vector space. Good? Clear? Okay. 6. Look at all the functions. You know functions, right? You're studying them in calculus, and you've met them before. All real valued functions, functions from R to R, for example. The set of all functions from R to R, any function that you want. It's a vector space. There's addition of functions, right, over R. There's addition of functions. You add two functions, you get a function. You can add them in whatever way you want. It's associative, right? Good? You can multiply a function by 3. You get a new function. All the distributive laws hold. If you multiply a function by 1, you get back the function. Do you agree? There's the 0 function, x equals 0. Right? Everybody good?
How is that example different from the example 5?
These are just polynomials. Here I'm taking all the functions. E to the x, sine x, arctan of x, all the functions, and many functions you've never thought of in your life, and many functions that don't even have a formula. Okay? Any function you want. Okay? All the functions, only real valued, that go from R to R. Do you agree that it's a vector space? Okay? Let's take it a step further. Well, I don't know if you've already encountered these notions in your calculus studies, but I'm going to mention them and just intuitively explain them if you haven't. Continuous functions. Okay? Continuous functions, intuitively, you're going to formalize this in calculus. Intuitively, continuous functions are functions that you can draw without lifting the pen off the board, or the pencil off the paper, or the marker off the air. No, that doesn't compile. So that's a continuous function. Continuous functions are also a vector space. You add two continuous functions, you get a continuous function. That's something that intuitively makes sense. It, of course, requires proof, and those proofs are in calculus. Okay? There's a notion of a differentiable function. A differentiable function is a function that has a derivative in every point. Okay, and intuitively you can think of a function whose graph doesn't have any cusps. It has a smooth graph, no. Okay? Differentiable functions are a vector space. If you add two differentiable functions, you get a differentiable function. Okay? So let's maybe call this 6 prime continuous functions. And let's call it 6 prime prime differentiable. Functions. If these words don't mean enough to you at the moment, don't worry about it. But when you get to calculus and encounter these notions, then you can flash back on this and say, hey, I know why continuous functions are a vector space, because one of the theorems you're going to prove is that if f is continuous and g is continuous, then f plus g is continuous. Okay? Good? So this is a very rich list of many, many things that you've encountered in mathematics, and the list goes on and on. We're going to stop here. It's just a list of examples, but we're going to I'll mention many more examples as we proceed, as we go along. Okay? So questions about all of this. Okay? So once again, to summarize, it's very abstract. It takes time to get used to seeing something that's completely abstract, but keep in mind the examples. Okay? Whenever you want to, suppose somebody asks you, is it true that in any vector space the following property holds? What do you do? How do you know if it's true, if it's false, if you want to prove it, if you want to give a counterexample? Well, you think examples. Okay? So if somebody tells you alpha times 0 is always 0, then you start thinking in examples. If you take alpha times the 0 polynomial, is it the 0 polynomial? Yeah. If you take alpha times a matrix, is it the zero matrix? Yeah. If you take alpha times a function, is it the zero function? Yeah. So it seems to work in all the examples. Well, probably it's true. Let's try proving it, right? And then you prove it using the axioms, okay? And if you find one of the examples where it doesn't work, so suppose somebody tells you that, I don't know, 6 times a function gives you the zero function, you say, 6 times v gives you v, then you're going to say, no, that's not true. 6 times a matrix is not the same matrix. It's a different matrix, right? There's a counterexample. Okay, good. That's how you approach these abstract things. You always think examples. Examples are where you feel more secure, where you know what you're doing, and then go one step up to the abstract. Okay, and don't be intimidated by the abstract, because you get used to it. Okay, we're going to do many, many things in the abstract, and gradually you'll get used to them. Okay, so what we're going to discuss next is the notion of subspaces, coming up next.